Welcome everyone to this week's HPL seminar, and this will be the last one of the year. We'll see everyone again in January. But today we've got Matt Zukowski, who's come to talk to us about speed skating. So Matt did his Bachelor's of Science in Kinesiology at the University of Calgary. And then in 2020, he started his MSc with Matt Jordan and Walter Herzog, focusing on neuromuscular determinants of skating performance. So Matt is also a strength and conditioning coach at CSI and head strength coach at the Olympic Oval Development Pathway. And in that position, he's been able to apply some of his methods from his thesis into the daily training environment for his athletes, some of whom are in the audience here today. So welcome, guys. So while Matt's been spending the last 2 years focused on skating performance, he says he can't skate, even in the slightest. And he's also an avid basketball fan, particularly the Portland Trail Blazers. But today, Matt will be talking to us about his master's work titled Assessing Speed Skating Performance, the Needs for Specificity.
Awesome. Thanks, Olivia. In an earlier version of this presentation, I actually had a video of me trying to skate. I realized this was going on YouTube and that slide quickly got deleted. But in all seriousness, I feel like that's always been an advantage because the skating motion is so unique. It's a curious form of locomotion that the human body wasn't designed to do. And I've never taken it for granted, so much so that I dedicated the last 3 years of my thesis looking at it. So with that, let's jump in with a little bit of background on long track speed skating for those of you who are less familiar with the sport. Long track is actually Canada's most prolific winter sport in terms of medals, accounting for over 40 medals at the Winter Olympics. However, we haven't won a medal in the 500 meters since 2002, and if my project could even play a minuscule part in helping with the next medal, that would be incredible. Current world records range from 33 to 36 seconds in the 500 meter event, which is the shortest distance we have. And what we do know is that the initial 100 meter split, which athletes and coaches will refer to as the opener, accounts for a large percent of variation in final placing. It's also when we have estimated the highest mechanical power output during initial acceleration, specifically the first few strides as athletes accelerate from a standstill from the start line. There's a definite threshold that you can identify if you want to place well in the 500 meter. Taking times from the World Cup last weekend, for the men, that was under 9.6 seconds. And for the women, that was under 10.6 seconds, which actually are quite comparable to the 100 meter sprint in track and field. Speaking of that event, this is a picture or a rendering of the 1896 Olympics and the 100 meter sprint. Clearly, track and field has been able to benefit from a growing body of research, and we've been able to hone in on biomechanical and physiological underpinnings of performance to the point where you would never see this amount of variation in starting positions today. In contrast, here are a few stills from the 2022 ISU World Cup. Now, my athletes in the audience there might bristle at me comparing them to the 1896 track and field Olympics, but the point I'm trying to illustrate is that there's still a lot we don't know about on-ice acceleration as athletes, coaches, and researchers, and the literature that we have looking at this is actually pretty sparse. In speed skating, there's 3 studies that I'm aware of that looked at the kinematics of the start, 2 of which actually happened before the clap skate was introduced, which dramatically increased performance. There are a few things we do know, though. So what's been well defined is that there are 2 discrete movement phases in the start, running and gliding. Running is the initial phase as athletes react to the gun and accelerate from a standstill at the start. And it can be characterized by shallower knee and hip angles, shorter ground contacts, and a more rearward application of force as athletes actually jump from skate to skate, propelling themselves horizontally down the ice. Now, at some point after around 15 to 20 meters, the forward velocity of the body center of mass reaches a point where you can no longer push backwards without the skate slipping on the ice. And that necessitates the transition to gliding, which can be characterized by deeper hip and knee flexion, a longer push-off that spans approximately 200 milliseconds and is directed more perpendicular to the direction of travel or laterally. The best way to appreciate this, though, is to see it. Before I play this video, mandatory plug, the athlete that you see at the top of your screen is Carolina Hiller, who I'm very fortunate to work with. currently the fastest woman in Canada at the moment. Tomorrow, she skates in the 500 meter at 110. Go cheer her on and plan your next 3D kinematic analysis of speed skating starts, because it's sorely needed. So in this first video, we can see the running phase quite well, where we see more of an upright torso. Athletes are actually jumping from skate to skate. And if I splice this with video of them running on the track, I'd be willing to wager that it wouldn't look much different in terms of positions and postures. The next video is taken from the same race, just from a different angle and taken out to 50 meters. And here we can see after the 6th or 7th stride, there we go. After the 6th or 7th stride, the athletes drop down, the torso becomes more horizontal to reduce the influence of air friction, and they start moving into that longer push off that gliding is characterized by. Presumably, given the contrast between these two phases, an athlete could perform better in one or the other. And if technique is equal, this will also presumably or comprehensively be underpinned by basic neuromuscular properties, such as the multi-joint force-velocity relationship or torque joint angle relationships. This brings us to the principle of specificity, which is a really commonly accepted training principle in the area of strength conditioning. Almost universally, if you open any strength conditioning textbook, it's going to discuss the notion that at certain times of the year, we should program movements that are specific in terms of postures, ranges of motion, velocities, and contraction type. However, the research supporting this in terms of multi-joint complex movements that we observe across different sports is actually quite sparse. Certainly, we understand that if we're training in an isokinetic dynamometer at a different angular velocity or a certain joint angle, we can expect to see the greatest improvement under those same conditions. Or I know that if I'm going to be testing a runner in an incremental test, I may want to opt for testing them on the treadmill versus testing them on the bike. But in terms of complex movements in applied sport performance settings, we actually don't have a good understanding of the influence of test specificity and whether it predicts or whether it impacts predictive validity in skating athletes or any athletes in general. Speed skating just happens to be a really convenient model to study that because of the controlled competition environment and our current lack of knowledge. So the overarching goal of my thesis is to develop two specific jump tests, which you can see on the left of the slide here. The first one meant to mimic the gliding phase. The second one meant to mimic the running phase, and compare them to a gold standard test, in the case of this thesis, the vertical jump, in order to understand the impacts of predictive validity, trying to consider the two movement phases. Before we jump into the data, the last thing that we have to discuss is how to select a sport performance test. So a primary goal of this thesis was to develop things that I could actually implement with athletes and coaches. I was selfish, which meant that at times I sacrificed internal validity for external validity, and I prioritized things that were feasible and that I could implement in a timely manner with athletes. Working with athletes, you soon learn you never have enough time or as much as you'd like. But as we move throughout and I present all this data, I hope you'll find I've also done the work to look at validity and reliability as best I can. Which brings us to the first study. It is part of my thesis titled Single Leg Lateral and Horizontal Jump Testing, Reliability and Correlation with Long Track Sprint Speed Skating Performance. Methods. We recruited 26 long track speed skaters, 16 males and 10 females. They were all national level athletes with a training age of greater than 5 years. Like we mentioned, we developed two specific tests to try to mimic the running phase and the gliding phase respectively. This is the single leg horizontal jump test. And this is the single leg lateral jump test. Now, we used a robotic resistance device, which we attached to a waist harness on the athletes to apply loads of 10 newtons, 7.5% of body weight relative to body mass and external load, and 15% of body weight. And this robotic resistance device that we used also had a linear encoder, which allowed us to look at peak velocity achieved under each jump condition. Athletes were familiarized and then came for 2 subsequent test days. So on each day, they would perform the same protocol, either the lateral jump or the horizontal jump, twice in a row, separated by 20 minutes of rest in order to assess intra-day reliability. All this testing was held during the early 21 to 2022 season, during which there were 3 local competitions at the Olympic Oval. The best 500-meter time each athlete skated was pulled, which allowed us to look at correlations to performance as well as reliability. Beginning with the reliability results, we used intra-class correlation coefficients, within subject coefficient of variation, as well as bland Altman analysis to look at reliability. And our findings were that all of our tests under all of the load conditions displayed acceptable to good reliability with ICCs of greater than 0.8, coefficients of variation of less than 5%. Moving to correlations with on-ice performance, to try to orient you to what you're looking at. On the y-axis, we have peak velocity under each jump and/or load condition measured with our robotic resistance device. On the x-axis, we have 100-meter time, which we normalized by percentage of the sex-specific world record in order to include both males and females in a single analysis. So on the top, we have the horizontal jump. On the bottom, we have the lateral jump, and the loads go from lightest condition to heaviest condition as we move from left to right. We found significant correlations under all jump and load conditions, but what was really interesting was the trends that we see. So the horizontal jump trended towards stronger relationships at the lightest loads versus the lateral jump trending towards stronger relationships at the heavier loads. And this may speak to some velocity specificity, considering that the horizontal jump under the 10 Newton condition, which is essentially body weight, could be argued that that's the most specific to the running phase when we see shorter contact times and ultimately higher movement velocities. Inversely, we know that during gliding, we have a longer push off, and it could be that loaded conditions better captured this. Moving forward, this plot's the same, except now we have 400-meter lap time instead of 100-meter time. Similar patterns, just slightly weaker relationships, because once we move to the 400-meter lap, we have some confounders such as how athletes skate in the corners, how they deal with competition, and inevitable fatigue as they get to the end of the race. This is individual data from all the males in the sample, showing individual profiles for both the horizontal jump and the lateral jump, which I wanted to include to illustrate that a high peak velocity under one jump or load condition doesn't necessarily guarantee success in another. In this manner, we could profile athletes to start to provide a directionality to training prescription. Another wrinkle that we wanted to investigate based on this was the feasibility of applying linear modeling approaches, which Franzi talked about a little bit last week in our bobsledding presentation. But a really common method in tests like this is just applying a simple linear regression and actually extrapolating out to the X and Y intercepts. Those values are often reported as opposed to the direct measures, such as peak velocity. So things like slope of the line, theoretical maximum load, or theoretical maximum velocity. So we use the same approach to look at the reliability of those parameters, which we found to be extremely poor. Albeit this is sort of an extreme example, because when you're running a single leg jump test, it necessitates a relatively narrow range of loads. You soon reach a point where you're knocking the athlete over, they can no longer balance. But I think it is an interesting cautionary tale, because in applied sport performance settings, when we're doing these tests with jumping and running, we often blindly assume a linear relationship, even though during these kinds of movements, by the very nature of them, we sort of can only assess the midpoint of the relationship instead of the disparate ends where we may expect non-linearities. So conclusions from that initial work: the lateral jump and the horizontal jump were both sufficiently reliable for performance testing in speed skaters. They both warrant consideration in a neuromuscular test battery. We should apply linear load velocity models with caution and instead consider reporting direct measures, i.e. velocity versus external load, which we used in the present study. And a limitation was that the use of competition time splits, so the 100-meter and the 400-meter, really limited the inferences we could make about each test and how it related to the independent acceleration phases. Which brings us to the second study, modeling the speed skating sprint start. This was dedicated to addressing this limitation and evaluating methods to better model and characterize the speed skating sprint start with respect to those two independent movement phases. Starting with what has already been done in other sports, we look to mono-exponential models, which are a valid and accepted way of modeling sprints over short distances. This was first introduced by A.V. Hill, Furusawa, and Parkinson in 1927. And since then, the equation's been simplified by others such as Ken Clark, Pierre Sarmazino, J.B. Marin, and Mladen Jovanovic to the one that you see below you on the screen. So given velocity at any point in time, if I know the maximal sprint speed that an athlete reaches, I can solve for tau, which is a time constant that equates to roughly 63% of max speed. So the time at which an athlete reaches 63% of max speed. And using that, I can model the entire velocity time or velocity position curve. A big limitation of trying to apply this in speed skating is illustrated in the graph here. In the solid black line, you can see the velocity time curve for an Olympic sprinter. In the dashed line, we see the velocity time curve for an Olympic speed skater. So speed skating has a very prolonged acceleration phase, with athletes often not hitting max velocity until somewhere around 250 meters into the race. Because of this, we weren't sure how this model would fit our raw data, so we sought to evaluate it. This time, we recruited 36 long track speed skaters that range from national to international level. So again, skaters that are skating Canada Cups to skaters that are skating World Cups or were in the Olympics last year. This was integrated into weekly training. So every Monday at the Olympic Oval, there's a 45-minute block of time dedicated to only start training. This is when I would set up over the course of a month, trying to collect as many trials as I could from the athletes. Here is a video of that data collection. Again, there we can see the robotic resistance device that we use called the 1080 Sprint. It has a 90-meter cable. And the way this worked is, again, the athletes wore a waist harness. We would hook up the cable to them. We had the machine on 10 newtons, which is the minimal functional resistance needed. And we instructed them to perform a 60-meter all-out start. At 60 meters, we placed a cone or a marker, which signaled to them that that was the time to eject, giving them 30 meters to hit the eject button, let the belt fall to the ice. And we took the first 50 meters for analysis to try to filter out any unconscious deceleration. Velocity was sampled at a frequency of 333 hertz. And with this data, we looked to evaluate the mono-exponential model fit, as well as the intraday reliability of model parameters with 31 paired samples. And then finally, we looked at the discriminants and the predictive validity using competition data similar to the first study, as this was also held in the early 2022 to 2023 season. Here's an example of our model. So in the dash lines, you can see the raw velocity data from the 1080. In the solid red line, you can see our modeled data. Up at the top, we have MSS, which in our case stands for maximal skating speed at 50 meters. We can see where tau occurs. So in the case of this athlete, just after 2 seconds. And we can see an additional parameter, MAC, or maximal acceleration, which we calculated as MSS divided by tau. And what that represents is the slope of the velocity line at time equals 0, which we're proposing as sort of a parameter that indicates performance during the running phase of skating. Here are more examples of model data for skaters that reach different maximal speeds. The mean R squared for all models built from this raw data was 0.97, and we had 62 on-ice repetitions. and all samples had a model fit of over 0.94. Moving to reliability of the different parameters, we use the same approach as study one, and we can see that MSS presented with excellent reliability, MAC good reliability, and tau had acceptable reliability. Encouraged by all this, the next step was to investigate whether these model parameters could actually discriminate between different groups of athletes in a very homogeneous sample. So we pulled the season best 100-meter time for each athlete. We split the males by tertiles. So the 33.3% that had the fastest season best 100-meter time were placed into our faster group. The 33.3% in the middle were removed to prevent instances where there was only hundredths of a second separating athletes between the groups. And the 33.3% that were the slowest were placed in the slower group. For females, we had a smaller sample, so instead we had to split by the median, which is a limitation. But nonetheless, using a paired sample t-test, we see significant differences in both the faster and slower athletes for male and female. I need to emphasize that though I labeled them as faster and slower, this is a very homogeneous sample of athletes. They're elite, they're well-trained, and they're all very fast. Next, we use the same approach with MAC, but because we're proposing this as a parameter to characterize the running phase, instead we split them based on time to 15 meters. Otherwise, same approach, splitting them by median and tertile. Here we see a limitation of the way we had to split for the females, where we definitely have some outliers which may have impacted the results. But looking at the males, we again see a significant difference, which is suggesting to us that these parameters are doing what they need to. They seem to be a feasible method to capture performance between each respective phase. Finally, to start to explore predictive validity with the entire 100-meter competition opener, we built a series of linear models, beginning with MSS and MAC as independent predictors. We ultimately landed on this one that you see here, as we found MSS and MAC to both be significant in our model, where we see high predictive validity with on-ice 100-meter competition splits. So conclusions from this, mono-exponential modeling does provide a sufficient fit of the long track sprint start velocity curve. The extracted parameters, MSS and MAC, are both reliable and valid. And we propose this as a very intuitive and feasible method of monitoring start performance. I get really excited by the raw data, but when you try to present it to athletes, or coaches, they get overwhelmed pretty quickly. Being able to report two simple numbers, I think, is very powerful. Now, the last component of my thesis, unfortunately, I don't have all the data collected, but that'll be taking the two parameters that I showed you, the different on-ice tests, and trying to examine them relative to my off-ice test to evaluate the influence of specificity. But because I don't have that, allow me to put my strength coach hat back on for 5 minutes and present a case study to try to tell you why this matters, or show you why this matters. So the data I'm about to present here is from 2 elite 500-meter female sprinters. They're both currently ranked top 25 in the world, so not bad. All good. Okay, so 2 different athletes. First, we see athlete A has a much higher rate of initial acceleration, as we can see in the velocity time curves, as well as the model parameters below. She gets to 63% of her maximal skating speed half a second faster, almost. Whereas athlete B ultimately reaches a higher maximal speed, but does so slower. And that's actually reflected in the competition results, where we see athlete A has a faster opener, but athlete B actually has the faster lap time. Moving to some jump results. Unfortunately, I don't have the lateral jump for both of these athletes collected yet. So on the bottom, you see the single leg horizontal jump test that I've showed you. And on the top, you see a loaded counter movement jump test, which is performed like so. So this is the gold standard method that I'm trying to compare my more specific tests against. And in this test, we test the athlete at loads of body weight, 30% of body weight and 60% of body weight, because in bilateral movements, we're able to load a bit more. Now we see that in the single leg horizontal jump, athlete A, who we know to be a better accelerator on ice, presumably a better performer during the running phase, has much higher performance at every load. And in the counter movement jump, we actually see the inverse. So what are the differences between these two jump tests? Again, we understand that the single leg horizontal jump, I'm in a relatively shallower knee and hip position, more similar to the running phase, versus something like a counter movement jump, where my counter movement depth is going to be around 35 to 40 centimeters. I'm probably reaching a knee angle that's going to be a lot more similar to the gliding phase of skating. So based on this, how could this actually start to impact training? One of these athletes I work with, and this is real world examples of implementations that we made, of program interventions we made with coaches. The other athlete, this is sort of hypothetical, but athlete A, who we remember seems to have a deficiency in late acceleration or perhaps the gliding phase. Sport-specific training, we might implement glide-specific cable work pre-ice, so working on efficient force application during that gliding phase. And once we get on ice, we might be working on lightly resisted roll starts. So having them start from a rolling position, light resistance to kind of teach the athlete to continue accelerating later into the phase. For athlete B, who had that deficiency in the running phase, presumably, maybe we look at implementing 15-meter stand starts, and instead we actually consider changing the start position based on that deficiency. From an S&C side, for athlete A, perhaps we prioritize strength in deeper joint angles, as well as jumps with a longer push-off duration. And for athlete B, strength at shallower angles and increasing sprint volume off ice. And then from a physio perspective, for athlete A, perhaps we want to assess hip and ankle range of motion to ensure that they don't have any deficits or any blockages that are preventing them from being efficient in that gliding phase. Versus for athlete B, we may want to assess terminal hip extension and look at optimizing the adductor to abductor strength ratio so that they can handle the increased start volume that we would be exposing them to. And here are my references from today, and ending with acknowledgements. So thanks to my supervisors, oval athletes and Speed Skating Canada, who have been so gracious with their time in helping me out and do all this work. I'm really proud that if any of this does get published, this will be the largest study on long track speed skaters ever conducted, as well as the CSI Calgary, my colleagues, and committee members.
So, questions?
Sure, yeah. You said the loaded counter movement jump is currently what you're trying to assess against?
Yes.
So they use that currently to predict performance?
So currently in the literature, the primary tests have been the Wingate protocol on a cycloergometer, which I would argue lacks specificity with speed skating and the complete knee extension that we see. And the other test that's been used is body weight counter movement jumps. But at the Oval and with Speed Skating Canada, we do have internal data that suggests a stronger relationship with that loaded counter movement jump test.
So how good are what is the predictive capability of the two tests? Like how good are
Of my specific tests?
No, these other two that are currently used, like the Wingate and this.
So similar, the correlation coefficients would be similar to the ones that I presented in my two tests. But again, a limitation of all of this is that we're just taking a broad 100-meter split, which could be composed of running and gliding. We don't really understand the proportion of each or how that interacts with each skater's individual technique. So similar thus far.
What do you mean by efficient versus non-efficient? Like what is non-efficient force application during the gliding phase?
Yes, so if you read the literature, you want, during the gliding phase specifically, you want to be able to direct your force as horizontally as you can, right? So that's primarily achieved, or you want to maximize work per stroke is what it comes down to. So that's achieved by putting more force into the ice or being more efficient with your application of force. So exerting it as horizontally as you can, trying to minimize vertical force.
Are there instrumented skates to measure this?
No, not that I'm aware of. There's some studies in the 80s that use strain gauges, but that was just forces versus horizontal and vertical force. And that was done before the collapse gate, which obviously changed some of the kinematics. So.
I have
Yes.
one quick question. So you said, if I remember correctly, the peak velocity of 500 wasn't often hit until like 250 meters kind of thing.
Yep.
How much of that is pacing versus like physical limitations? Like if you get a 250 meter race or whatever, like would they be able to hit peak velocity and where?
I mean,
Could
model.
skaters answer too, I guess?
Yeah, the skaters could answer. It'd be interesting. Modeling research indicates the best strategy is an all-out strategy.
Okay.
In the 500 meter. So the fatigue at the end is kind of inevitable, but
Yeah.
the best strategy is all out versus trying to pace yourself.
Okay.
Thoughts?
Yeah.
Yes.
Okay.
Do you think you could go faster in a 250 meter race, or would it be the same?
It would be the same because we build all of our speed through the turns, right? After 100 meters, you can only go so fast on the ice. Where in the corners is where we actually build all of our speed.
Straight from the horse's mouth.
Thank you.
I have quite the same thought about the effect of kind of the strategy. I was so fascinated by the correlation that you showed between the vertical, horizontal speed, horizontal jump, and performance. And how much how much of the variability was that? 80%?
Let's see. 80%, I believe. And that wasn't an R squared, that was just a correlation coefficient, but there we go.
Yeah, so going back to track and field, if you're going for an 800 run, the strategy pacing is probably one of the most important things for 400. I'm just wondering, in terms of speed skating, seems like that one specific variable explains quite a lot of the variance in the any thought on that?
You mean the horizontal jump test that I presented here? Yeah, I think it's interesting and sort of counterintuitive that we see higher correlation coefficients in the horizontal jump versus the lateral jump, because one would argue that the lateral jump is more specific to speed skating. I think one thing that's interesting as well when we look at these individual profiles is the slope of the line for the lateral jump is relatively shallow. And it's almost flat in some cases for some of the athletes. Like if we look right here, it's flat. So it could be that the loads I used in this study, so 10 newtons, 7.5% and 15%, were inadequate to really start to tease out differences, because these athletes do a ton of training in the frontal plane with different cables, turn cables, really heavy resisted movements. And it could be that a single leg unilateral jump just wasn't adequate. And I might want to, in the future, we might want to move towards something like an isokinetic push where you have a little bit more support and you can really start to tease out some of those differences better. Would be my hunch. Or maybe the biggest factor is just that sprinting phase and the ability to displace yourself horizontally off the line.
Because I know nothing about skating. Is there any skill level that would change the performance? That based on what I see, that 80% of the 70% of the performance comes from this one ability to propel yourself, accelerate forward. Is there where is the effect of pacing? Where is the effect of skill level, or do you think they're also part of this?
Well, first, what I'm presenting here is a 100-meter time split. So in the 100-meter, there is no pacing, essentially. They're trying to reach the 100 meters as fast as they can. So that's all out. It's certainly a technical movement. And I think that's why MAC in my mono exponential model could actually be an interesting parameter where, like I suggested in the case study, if you have a deficiency in MAC, maybe that's something where you want to begin playing with different starting techniques, right? or playing with your strategy over those first 15 meters. And talking to coaches and athletes, that's something you'll hear commonly, is that an athlete's running too long or that they're starting to glide too early. And we really don't understand the best strategy to cover the first 100 meters right now because the work hasn't been done. Yes.
All right, can you go back to the one where you have like the 5 different curves, fastest skater, slowest
Yes.
skater? It's kind of like, this is like all within 10 meters in this first part, you get like real divergence. I'm assuming in the first meter, they look effectively the same.
Yeah.
The acceleration. So what's the difference when you get to like 2 meters? Why do they start diverging there? What is it about these different athletes that result in this?
That's a
'Cause
good.
those two are like way different than the other
Yeah.
5.
Yeah.
4.
That's a good question. And I could look into the raw data and start to see what's happening at 2 meters. I hadn't specifically thought about that. It could be, and this is another thing that I didn't really mention in my presentation, but presumably what hasn't been well defined is the transition point, right, between running and gliding. So that would occur on a spectrum. It's not I'm running and then all of a sudden I'm gliding all within 1 meter. We don't really know when that happens. We don't really know how long that occurs. So that could be a result of strategy as well. Maybe those athletes are trying to glide too soon, sit down low, and because of that, they don't have effective horizontal force application. That's one hunch, but it's certainly something to look at.
Yeah, and I guess I wonder if this kind of goes back to this like functional force velocity thing, where this can
Yeah.
tease out these issues here, or maybe some of your like the like jumping things where you have to
Yes.
turn off the load. I guess would work the same way.
Yes.
Have you done like force velocity profiling with the 1080 with the sprinter with the skaters?
No, I haven't. Not at different loads. So that I've played around with it a little bit. The problem is once you get to around 9 kilos off the start line, they're just completely slipping out and you have them face planting. So it's a pretty narrow range of loads when you're skating in an essentially frictionless environment.
Just to add to the comment there, one thing that I would look, the speed is going to be stride length times stride frequency.
Yeah.
One of the things that you might want to look at, how the top performers and the lower performers, how they differ. Is it that the top performer, that they all have about the same stride lengths, but the top performers do it at a higher frequency? And my hunch, that's not going to be the case. My hunch would be that maybe the frequency is very similar, but that the top performers, because they might have more power, take longer strides at the beginning and therefore might have that greater acceleration. That's one thing that you might want to look at. It's just the stride length times stride frequency, how that looks like for different performers.
Yeah, it'd be difficult to pull out of the raw data from the 1080 just because of the movement artifacts.
That's right, but
Unfortunately.
you didn't film that. So you don't have to.
Don't have film, no.
Well, but I also saw that you have these wiggles.
Yeah.
Would that potentially be good?
Potentially. I mean, if we just look at this raw curve here, I would guess that over the first second, we see 2 pretty distinct strokes, right? Or strides. And then from second 1 to 2, 1, 2, 3, 3.
So I think if you counted wiggles or if you superimpose the wiggles rather than the smooth curves, maybe that would give you a little bit of additional information. Just seeing, somebody has the wiggles further apart, presumably taking longer strides.
Yeah.
That type of stuff.
Yeah, Andrew.
So have you looked at all into like your change in velocity within those wiggles? So I think that would be at some levels interesting to look into because it kind of gives you a stride frequency for the athlete.
Yeah.
But it would also like on each push, how much extra speed do they gain off of each push? And then you could also probably tease out to get some video to go with it, right and left leg deficits.
Yeah. No, I agree. That'd be interesting. One thing about these models that's really attractive to me, though, is that you could do this with timing gates, right? I'm using the 1080, but this approach has been used in timing gates with sprinting. And like I said, it's intuitable. It's very feasible. Athletes understand it. Coaches understand it. And once we get into some of those analyses, it's less likely to be used in the real world, which is
But I think
Con,
you
but
could
yeah.
get something more complex, but then
Distill it down, yeah.
Distill it down, like, because if you could tell someone, hey, your left leg push off every stride on your left leg is worse.
Yeah.
Coaches would like that.
So what's going on here where you get this pretty regular shift where it's like one is high, like after this, what I'm assuming is when they transition after like 4 seconds or something, you start seeing this irregular signal where one
Yeah.
goes irregular.
So to me, what I think that is the transition from running to gliding, where you start to see those sort of leaks. The other thing though, is it could be as they get further away from the machine and as they build velocity, we're just getting more oscillations of the cable, and those are just movement artifacts. Yes.
Could you talk a little bit more about your measurement system? You
Yes.
were mentioning robotic resistive device. But what does it really measure, and does it feel like you are getting to the vector?
Yes, so it's called a 1080 Sprint. It's a robotic resistance machine. It has a servo motor similar to like a Humac norm, which allows you to apply horizontal loads. If you have heavier than 10 newtons of resistance, the manufacturer also says, also indicates that you can take kinetic measures, so force, power, things of that nature. I haven't looked at that a ton. I've been using it more as a linear encoder to continuously measure velocity. And using it in that way, the minimum functional resistance is 10 newtons, so 1 kilo. I haven't quantified how much that's slowing athletes down, but certainly I would guess that it does to at least some degree. And the males usually don't feel it, like they feel like they're just skating with a belt. But sometimes lighter athletes will make the comment that they do feel like it's pulling them back a little bit.
So is it, does the direction of the force change? Because it seems like it is a little bit going downwards right now.
Yeah, so this is earlier in my data collection, this picture, but I tried to standardize the angle change by setting up athletes 5 meters away from the machine when I collected all this data. This was just the picture I used, but yes. Yeah, all you're getting is horizontal. So as the cable is getting pulled out, the linear encoder is giving you position time, and from that, that's how we get velocity. So it's only horizontal measurements.
This is for them. Sort of.
Good.
How do you choose the starting position?
It's all down to the person. Like you look at everybody and everybody will set up different. Like you can see between the two athletes in these photos, their position, they're just looking at their 2 foot positions, they're different.
Whatever is most comfortable to you, and also the functionality of it, of getting off the line, feeling as quick as you can.
How often do you change the position? Ever? Or
Like in practices, we try to tweak it with like once a week at least. Like you look at it and see how you're feeling with it, coach feedback. Major changes, not quite often, unless something's going really wrong, where you're feeling like the start's just not happening for you. But usually it kind of stays over time.
It's more of a set it, forget it movement than constantly tweaking it.
yeah.
Matt, I'll just ask a quick question, building off what Walter said, but if you wanted to know a little bit more about what's happening stride by stride, just the position time data, the position, or even because I think you position
Versus time.
Your distance even. I think like there's a function in there where you can look at 0 to 50 meters. Is there any way that you've looked at, been able to kind of extract out what's happening?
Not explicitly, no. And I could look into that. I have looked at force over time to try and pull out contact times or push off times. And it seems like maybe that's feasible, but again, I'm not confident in it. And you would need to confirm it or validate it using something like 3D motion analysis or IMUs or something that nature.
If there's a way, not that obviously video is great, but there's some way that you can either overlay the curves you have, the wiggles with each other, and compare the wiggles between different athletes. That's it. Well, that's fine.
So I asked you that before, but the 10 newtons. So if I'm going at full speed, which I guess is what, 15, 16 meters per second?
Yeah.
What's the air resistance? What's the air resistive force? And is that comparable to your 10 newtons, or is it much bigger, or is it much smaller?
Still need to look
Still
into
don't
that.
know.
Yes.
Does anybody know what air resistance of an average speed skater is when you go at full speed
That's a really,
in terms of force?
it would change from rink to rink. So like we just came back from BC and you can feel a difference just because it is
Yeah,
lower.
you're at higher altitude.
Yeah.
In Calgary.
Yeah, so that would change from rink to rink, but I don't think we have those specific numbers as athletes.
That would be fairly easy to calculate.
I'll have that for you the next time I see you.
Everything, you need to make an estimate of what the frontal area is, but you could make a fairly good estimate, or a rough estimate. I mean, people change their body shape with every stride, so that differs a little. I'm curious about, is the 10 newtons, is that air resistance at full speed, or is it 10% of it, or is it 200% of it? I have no feeling.
Just to add on
Oh
to,
yeah, good. He knows it.
if no, I know.
He'll solve it.
But if we got any of the guys into a wind tunnel, we could get their coefficient of drag, and from that calculate their resistance
That's right, we need to
across
drag
speeds.
resistance with the suit and everything.
Yeah, so that really just depends on their specific body positions at a couple of different positions. And you can get that data. You just need a wind tunnel.
Drag the frontal area.
So sort of their specific 3D geometry, so where their arms and legs are, it really matters for that, but you can get that.
The wind tunnel in Calgary.
Carlton has one big enough for these guys.
Can we estimate the number for that? Based on
I could tell you for a sphere.
You probably could get a number.
Yeah.
Because I would assume that alpine downhill racers would have similar suits to speed skaters. And I know data of air resistance is available for, like coefficients of drag are available for alpine ski races, and that might be
that's what I'm saying, like,
similar.
we don't need to do the entire experiment.
But I'm sure someone has drag coefficients for humans in different positions.
Yeah.
Not necessarily specific to.
Yeah, but we need to have those slippery.
Yeah, you need to have their
Suits,
materials.
Our coach actually did some wind tunnel tests. I don't know what year that was in the 90s, but for sure if you looked into something with like in the 90s of wind tunnel, he was doing some.
Okay.
But
You can easily turn that data into drag coefficients.
I mean, the national team does their suit testing every year, right, in Ottawa at the.
Which brings me up to the fun question for the day. Who was the first person to skate in a super tight suit?
You stumped them.
It was a guy called Crayon, and Crayon is a very Swiss name. He's actually a Swiss guy, although they are not really very good speed skaters. This is a guy who was lived like drank a lot and smoked a lot. And then he was about 40, started speed skating, and then started speed skating in World Cups. And the reason why initially he could keep up is because he was playing with skates and suits and so, and had always the best equipment homemade. And so he had never really won anything, like 15s in a World Cup or so. It's just okay, Anyway, just fun question.
I also had a question about the run to glide transition. Did you say that decision is often based on, like, when you reach the point where the skate will start slipping?
Yes.
So maybe, I don't know who this is a question for, but if the skate slips, can the athlete recover, or is it like game over?
Depends on how severe the slip is, because national championships this year skating for a World Cup spot. I slipped in the second step, almost ended up on my face, and instead of opening in 100 meters in 9.9, I opened it in 10.6 and threw the World Cup spot away. So it's all relative to how severe the slip is. Some can be super minor, and some can be a toe in and you lose your two front teeth on the ice.
And related to that, so there is modeling research. It suggests a velocity of around 6.7 meters per second is sort of the optimal time to start to transition, because that's when you are starting to get more slippage. I do wonder though, whether there's instances where if you have an athlete who's very good in that running phase, whether they wouldn't want to run a little bit longer and emphasize their strengths versus someone who's really good at gliding, whether they wouldn't want to try to transition sooner. And you certainly do see those differences in strategies just watching the World Cups. Some athletes look like they're running a lot longer. Some athletes try to sit down and glide almost off the line, which would be interesting to optimize using these tests.
So, oh, sorry. So when you said that, you know, in the study where you took a bunch of athletes and then you took the top third and the bottom third, and, you know, you found these very distinct differences, but you said, you know, they are all elite, they're actually fairly homogeneous. Like, how homogeneous are they? If you give me the 100-meter times, what range are we talking? Like, where would the slower ones be in their 100-meter times? Where would the faster ones be?
So for the males, the faster group would all be under 10 seconds in their 100-meter times, so 9.7 to 9.9. And then the slower group would be 10.2 to 10.4 approximately.
So 9.8, 9.9, 10.3, 10.4. So that's about, you know, maybe 5 or 6 tenths. So that's about 5 or 6%.
Mm-hmm.
So that's a big difference to me.
Yeah.
In elite sport.
In elite sport, yeah. I was just trying to make the point that I'm not taking novice athletes and comparing them to Olympians, but yes.
Okay.
The females would be a little bit closer too because of the way I split it. But
And so then the numbers that you have there.
is the modeled maximal skating speed at 50 meters.
So then you have a 10.5 and about an 11.2 or 3 on average. 10.5 to 11.3, 0.8 out of 10. So you get about a 7 or 8% difference there in that value. So that's similar in magnitude to what we actually have.
I have one question. First of all, I think like all this modeling stuff is super cool, but as far as like practical applications and kind of information that coaches might be able to use, like I'm assuming that coaches already take like split times or have like laser times from training or things like that, and can kind of look at like individual strengths and weaknesses off that. I'm assuming so. But like, so for example, like if you had a speed skater and say, okay, well his 15-meter sprint time is like comparatively slow, versus another coach who had the model something, their MAC is lower than they should be or something like that. Does the modeling approach provide like more information that a coach could use to then better prescribe training?
Yeah, it does. I don't think necessarily. I think you could get some of the same information. However, I've worked with around 20 coaches. I can think of one that's ever attempted to break up that initial 100 meters into a smaller segment, which is crazy to me.
Yeah.
The only time they measure starts versus video in practice is competitions.
Okay.
So they have no way to characterize performance during those two phases. And it just happened that with the 1080, it was really convenient working with the national team in the oval program. It's easy to set up. You don't need to set up timing gates. There's just an efficient way to do it.
So I was intrigued by the one example that you showed, you know, where the one person had the faster start over the first 100 meters, but then the other one had the better lap time. So we talked a lot about the start, but what makes somebody a good finisher, you know, a 400 meter after you have done the first 100? Have people looked into that, you know?
Not really, no. Presumably more work per stroke during the gliding phase, but certainly fatigue does become a factor during the lap. So perhaps they're fatiguing less as well, or able to maintain that a little bit better. there's also a skill of skating the corners. So track patterns come into play and things like that as well.
So maybe question to the skater, it always seems, well, in the old days, there was only one 500 meter for the Olympic Games, yeah, and now there is two, you get an inner and an outer. And does that make a big difference when you have that second curve on the inside? It just seems more difficult. They're usually slower.
I'm pretty sure they're back to one at the Olympics.
Yeah, we are back.
Oh, back to
After
one.
2014 or 2010, they went back to just one.
Is that fair?
You're skating the same distance.
Yeah.
You're skating the same distance, but when they started introducing that, it always seemed, well, more often than not, if you have the second curve as an outer, when you're tired and at full speed, that seemed to be an advantage compared to when you have the inner. And I remember the Olympic Games in 1988, and nobody had ever skated at 1,000 meter altitude, and especially the men, everybody who had the inner completely lost it. They came into the other lane because they just couldn't hold it. They were not used to skating like that, but that's not the case anymore. Like, people are better prepared for that.
People fall on the inner, like if somebody's gonna fall in this control, it'll be on the inner lane. But I guess world-class athletes they still do fall, but they skate the inner a bit differently. So you have to go in. It gets a lot more complicated to personalization. It's like, I know I struggle with the inner a bit more, but it just comes down to myself and my technique. But these two guys, I know that they can hit their inners very well.
So you think you skate equally fast, independent of what lane you draw?
Yes, I do myself. Looking at PVs, I've skated PVs both starting in the inner lane, finishing in the outer, and vice versa. And then here in Calgary, at high altitude, lots of glide in the ice, and you tend to build more speed throughout the race in the last 250, like Matt said, and then the human error just comes into play. How you set up your turn, how that race is going. No two races are the same, so there's that variable thrown in there.
But you wouldn't be desperate if you get drawn in the Olympic final. Like, you couldn't care which lane you draw.
No.
Interesting. Because in track and field, they assign lanes based on the preliminary rounds, and you get specific lanes in the 200 meter run or in the 400 meter run, depending on how you did. Nobody wants to have the inner lane in the 200, and that usually goes to the worst performer, the one that just made it into the final. So you're kind of not as good in the preliminary heat, and then you get what people consider a bad lane because curve is tighter. People think they cannot run quite as fast in that curve.
No, there's no such thing as a bad lane in this sport.
Good to know.
So you showed several types of jump tests that are directly related with the performance.
Yep.
If somebody just works on that test, let's say, like fine tune everything to like something a bit higher, would that improve the performance?
That would be the next question. So my feeling as a strength coach, if I see a deficit in a given test, like in the example of athlete B here, I would program that test. I would have them perform that movement and see if that helps to make a change. But I haven't got there yet. This is more of invalidation pilot work, but certainly the next question.
All right. Well, if you have no other questions, we'll take that again.